Electrons are moving through your device's circuits in ways that fundamentally cannot be predicted. Not because our instruments aren't good enough, and not because we haven't discovered the right equation yet, but because reality itself has built-in limits to what can be known. Werner Heisenberg discovered in 1927 that the universe has a constitutional ban on complete knowledge, and tonight, we're going to explore why this changes everything about existence itself. Now let's begin our journey into the heart of uncertainty, where the cosmos reveals its most fundamental secret. That ignorance isn't the opposite of knowledge. It's knowledge as most essential ingredient. Chapter 1. Quantum Foundation in 1927. A 26-year-old German physicist named Werner Heisenberg made a discovery that would forever change humanity's understanding of reality itself. Working at the University of Göttingen under the guidance of Max Born, Heisenberg was trying to solve a puzzle that had been haunting quantum mechanics since its inception. Why did the mathematics of quantum theory seem to forbid certain types of measurements? What he discovered wasn't just a mathematical curiosity, it was a fundamental law that governs the deepest level of reality. The story begins with a simple question that had been troubling physicists for decades. How do we actually measure the properties of an electron? In our everyday world, measurements seem straightforward. To find out where your car keys are, you look around until you see them. To measure their speed, you could watch how quickly they move from one place to another. But electrons don't behave like car keys. They are so small that the very act of looking at them, which requires bouncing light off them, fundamentally changes their behavior. It's like trying to measure the position of a soap bubble by throwing tennis balls at it. The measurement process itself becomes part of what you're measuring. Heisenberg realized that this wasn't just a practical problem that better technology could solve. It was revealing something profound about the nature of reality itself. When you try to measure an electron's position with extreme precision, you need to use light with a very short wavelength high-energy photons that can pinpoint exactly where the electron is. But that's the catch. These high-energy photons carry so much momentum that when they bounce off the electron, they kick it in unpredictable directions. The more precisely you determine where the electron was, the more you disturb its momentum, making it impossible to know where it's going. This led Heisenberg to formulate what became known as the uncertainty principle, mathematically expressed as xpp is greater than or equal to k2, where delta x represents uncertainty in position, p represents uncertainty in momentum, and k, a bar, is Planck's constant divided by 2. This deceptively simple equation contains one of the most profound insights in the history of human thought. There exists a fundamental limit to how precisely we can simultaneously know certain pairs of properties about any quantum system. But the implications go far deeper than just measurement problems. Heisenberg's principle reveals that uncertainty isn't something imposed on reality by our clumsy measuring instruments. It's woven into the very fabric of existence. The universe itself doesn't know the exact position and momentum of particles simultaneously. This isn't because the universe lacks intelligence or computational power. It's because these properties don't exist with definite values until they're measured. Reality, at its most fundamental level, is genuinely uncertain. Consider what this means for our understanding of existence. Before quantum mechanics, physicists believed in what Pierre-Simon Laplace had called the daemon, a hypothetical intelligence that could know the position and momentum of every particle in the universe and thereby predict the entire future with perfect accuracy. Laplace's daemon represented the ultimate dream of complete knowledge and perfect prediction. Heisenberg's uncertainty principle doesn't just kill Laplace's daemon, it proves that such a being is logically impossible. Not even an omniscient God could simultaneously know the exact position and momentum of an electron, because these properties don't simultaneously exist in definite form. The mathematical formulation reveals something even more startling. Planck's constant, the k in Heisenberg's equation, isn't just a number. It is a fundamental feature of reality that sets the scale at which uncertainty becomes significant. This constant is incredibly tiny by everyday standards, which is why we don't notice quantum uncertainty in our daily lives. Your uncertainty in knowing where your phone is and how fast it is moving is completely negligible compared to the size of your phone. But for particles like electrons, uncertainty becomes the dominant factor governing their behavior. This creates a remarkable picture of reality at its deepest level. Imagine the universe as a cosmic casino where certain bets can never be won, not because the house is cheating, but because the rules of the game make perfect knowledge logically impossible. Every time reality measures something about itself, when particles interact, when measurements are made, when quantum systems evolve, it must sacrifice knowledge about certain properties to gain knowledge about others. The universe is constantly making trades between different types of information, and these trades are governed by fundamental limits that no amount of technological sophistication can overcome. Heisenberg's work also revealed the deep connection between quantum mechanics and the nature of observation itself. The uncertainty principle emerges naturally from the wave-like properties of matter that Louis de Broglie had proposed just a few years earlier. When particles behave like waves, they become spread out over space, making their exact location fundamentally ambiguous. The more you try to confine a wave to a specific location, the more its wavelength and therefore its momentum becomes spread out across different possible values. This isn't a limitation of our measuring techniques. It's a fundamental property of wave-like entities. The experimental confirmation of Heisenberg's principle came through ingenious experiments designed to test the limits of quantum measurement. In 1949, Erwin Schrödinger and his colleagues demonstrated that attempts to measure electron positions with increasing precision inevitably led to increasing uncertainty in their momenta, exactly as Heisenberg's mathematics predicted. These weren't just laboratory curiosities. They were direct observations of reality's constitutional limits on information. What makes this discovery truly revolutionary is that it applies not just to position and momentum, but to many other pairs of properties throughout physics. Energy and time form another uncertainty pair. The more precisely you try to measure when something happens, the less precisely you can know how much energy is involved. This temporal uncertainty principle helps explain why virtual particles can briefly borrow energy from the vacuum of space, creating temporary fluctuations that would be impossible if energy conservation were perfectly enforced at every instant. Perhaps most remarkably, Heisenberg's uncertainty principle reveals that empty space itself is uncertain. Even in a perfect vacuum, with no matter or energy present, quantum fields fluctuate according to the uncertainty principle. These vacuum fluctuations represent the universe as fundamental restlessness, its constitutional inability to be completely at rest or completely defined. The ground state of reality is not stillness, but a constant, unpredictable dance of possibilities becoming actual and then dissolving back into potential. As we stand at this threshold of understanding, we begin to see that Heisenberg's discovery was just the beginning of a much deeper mystery. The uncertainty principle doesn't just describe a limitation on measurement. It reveals something profound about the nature of existence itself. Reality appears to be fundamentally probabilistic, operating on incomplete information, not just from our perspective as observers, but from its own internal perspective as a physical system. This foundation of quantum uncertainty creates the stage for even more remarkable discoveries about the limits of knowledge and the nature of reality. As we'll see, the uncertainty principle is intimately connected to some of the deepest mysteries in physics. The problem of quantum measurement, the role of consciousness in determining reality, and the ultimate question of whether the universe can ever fully understand itself. Chapter 2. Hidden Reality. Beneath the familiar world of objects and events, lies a hidden reality so strange that it challenges our most basic assumptions about existence itself. When Heisenberg's uncertainty principle was first discovered, physicists initially hoped it might be a temporary limitation. Perhaps there were hidden variables that, once discovered, would restore the comforting certainty of classical physics. What they found instead was that reality itself operates in ways that make our everyday experience of definite objects with clear properties a kind of elaborate illusion. The search for hidden variables began almost immediately after quantum mechanics was formulated. Albert Einstein, despite his crucial contributions to quantum theory, never accepted that uncertainty was fundamental to reality. His famous declaration that God does not play dice with the universe wasn't just a casual comment. It represented a deep philosophical conviction that beneath quantum uncertainty lay a more fundamental, deterministic reality. Einstein, along with Boris Podolsky and Nathan Rosen, proposed in 1935 that quantum mechanics must be incomplete, arguing that particles must have definite properties even when we're not measuring them. This led to one of the most profound thought experiments in the history of science, the EPR paradox, named after Einstein, Podolsky, and Rosen. They imagined two particles that had interacted and then separated by vast distances. According to quantum mechanics, measuring one particle would instantly determine certain properties of the other, regardless of the distance between them. Einstein called this spooky action at a distance and argued it proved that quantum mechanics couldn't be the complete description of reality. Surely, he reasoned, each particle must have predetermined properties that local measurements simply revealed rather than created. For 30 years, this remained a philosophical debate. Then, in 1964, Irish physicist John Stuart Bell changed everything. Working at CERN, Bell developed a mathematical theorem that would allow scientists to test whether hidden variables actually existed. Bell's theorem showed that if reality operated according to local hidden variables, if particles had definite properties determined by local factors, then certain statistical correlations between measurements would have to obey specific mathematical limits, now called Bell inequalities. The experimental test of Bell's theorem required technology that didn't exist in 1964, but by the 1970s and 1980s, physicists like Alain Aspect at the University of Paris-Sud were able to perform increasingly sophisticated tests. What they discovered was revolutionary. Quantum correlations consistently violated Bell inequalities, proving that local hidden variables cannot account for quantum behavior. The universe really doesn't store complete information about particle properties in advance. Reality is genuinely uncertain in a way that no underlying deterministic mechanism can explain. This discovery revealed something extraordinary about the nature of existence. Properties like electron spin don't have definite values until they re-measured. Before measurement, an electron exists in what quantum mechanics calls a superposition, a genuinely ambiguous state where it has the potential for multiple, different properties simultaneously. This isn't just uncertainty about what we'll find when we measure. It's genuine indeterminacy in the fabric of reality itself. Consider what this means for our understanding of existence. In our everyday experience, objects have definite properties, whether we're looking at them or not. Your coffee mug has a specific location, temperature, and color, even when you're not in the room. But at the quantum level, particles exist in probability clouds of potential properties that only collapse into definite states when interactions occur. Reality, at its most fundamental level, is more like a vast collection of possibilities that become actual only through the process of measurement and interaction. The implications extend far beyond individual particles. Quantum entanglement, the phenomenon that Einstein found so troubling, reveals that separated particles can share a kind of unified existence where measuring one instantly affects the other, regardless of distance. In 1997, Nicholas Gizon and his team at the University of Geneva demonstrated entanglement over distances of more than 10 kilometers, with the correlations occurring faster than light could travel between the measurement sites. This is uncommunication in any conventional sense. No information is transmitted, but it reveals that reality has a fundamentally non-local character that defies our intuitions about space and separation. Perhaps most remarkably, quantum mechanics suggests that the classical world we experience emerges from this hidden quantum reality through a process called decoherence. When quantum systems interact with their environment, which includes everything from air molecules to cosmic radiation, their delicate superposition states rapidly decohere into the definite classical properties we observe. The stability of our everyday world depends on the constant disruption of quantum uncertainty by environmental interference. This process helps explain why we don't notice quantum effects in daily life, but it also reveals something profound about the relationship between different levels of reality. The classical world isn't separate from quantum reality. It's what quantum reality looks like when viewed through the lens of environmental decoherence. Every object around you, from your smartphone to your own body, is ultimately a manifestation of quantum processes that have been stabilized through interaction with the surrounding environment. The hidden nature of quantum reality also connects to some of the deepest puzzles in physics. The measurement problem, why quantum superpositions collapse into definite states when measured, remains one of the most profound open questions in science. Some physicists, following Hugh Everett III's many worlds interpretation, propose that all possible measurement outcomes actually occur, creating parallel realities for each possibility. Others, like Roger Penrose, suggest that consciousness itself might play a fundamental role in collapsing quantum states. What we do know is that this hidden quantum reality operates according to principles that seem to violate our basic assumptions about information and causality. Quantum mechanics allows for what physicists call non-local correlations, connections between distant events that are stronger than any classical physics would permit. These correlations don't allow for faster-than-light communication, but they do reveal that the universe has a fundamentally holistic character where distant parts can be more intimately connected than classical physics would suggest. The discovery of quantum non-locality has also led to revolutionary new technologies. Quantum cryptography uses entangled particles to create unbreakable codes, relying on the fact that any attempt to intercept the quantum information would disturb the delicate correlations and reveal the presence of an eavesdropper. Quantum computing promises to harness superposition and entanglement to solve certain problems exponentially faster than classical computers ever could. But perhaps the most profound implication of hidden quantum reality is what it reveals about the nature of knowledge itself. If reality, at its most fundamental level, operates through probability and potentiality rather than definite facts, then the universe itself is constantly learning about its own state through the process of interaction and measurement. Each quantum measurement is, in a sense, the universe discovering something about itself that wasn't previously definite. This connects quantum mechanics to information theory in fascinating ways. Some physicists, like John Wheeler, propose that reality might be fundamentally informational, that it from bit rather than bit from it. In this view, the physical properties we observe might be emergent features of more fundamental information processing operations occurring at the quantum level. The uncertainty principle would then represent a fundamental limit on how much information reality can contain about itself. As we probe deeper into these mysteries, we encounter the profound question of whether consciousness itself might be connected to the peculiar features of quantum reality. Some researchers like Stuart Hameroff and Roger Penrose have proposed that consciousness might emerge from quantum processes in the brain's microtubules, suggesting that our subjective experience might be intimately connected to the uncertainty and non-locality that characterize quantum mechanics. This hidden reality challenges us to reconsider our most basic assumptions about existence, knowledge, and the relationship between mind and matter. As we'll see in our next exploration, the very act of trying to measure this hidden reality creates paradoxes that reveal even deeper mysteries about the nature of observation, consciousness, and the fundamental limits of what can be known. Chapter 3. Measurement Problem. At the heart of quantum mechanics lies a mystery so profound that it challenges our most basic understanding of what it means to observe reality. The measurement problem reveals that the very act of trying to gain knowledge about quantum systems fundamentally alters what we restudying in ways that create an unbridgeable gap between the observer and the observed. This isn't just a technical issue about scientific instruments. It has a deep puzzle about the nature of reality itself and the role that consciousness might play in determining what exists. The measurement problem emerges from a fundamental tension within quantum mechanics. The theory describes quantum systems as evolving according to the Schrödinger equation, which governs how probability waves change over time. According to this equation, quantum systems exist in superpositions of multiple possible states, evolving deterministically as probability clouds that spread and interfere with each other. But when we actually measure a quantum system, we always find it in a definite state. The electron is here or there. The photon is polarized this way or that way. The theory that perfectly predicts statistical outcomes seems unable to explain why individual measurements yield specific, definite results. This paradox was crystallized in 1935 by Erwin Schrödinger through his famous thought experiment involving a cat that is simultaneously alive and dead. Schrödinger wasn't trying to be whimsical. He was highlighting the absurdity that seemed to emerge when quantum mechanics was applied to larger systems. If a quantum particle in superposition could trigger a mechanism that either killed or spared a cat, then, according to quantum mechanics, the cat should exist in a superposition of being alive and dead until someone opened the box to observe it. But this violates our everyday experience that cats are either alive or dead, never both simultaneously. The measurement problem forces us to confront a fundamental question: what counts as a measurement? In quantum mechanics, a measurement isn't just a passive observation. It is an active intervention that forces a quantum system to choose one of its possible states. But what physical process constitutes this choice? When exactly does the quantum superposition collapse into a definite classical state? And most mysteriously of all, does consciousness play a role in this collapse, or does it happen automatically through physical processes we don't yet understand? Different physicists have proposed radically different solutions to this puzzle, each with profound implications for our understanding of reality. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg in the 1920s, suggests that quantum mechanics is complete as it stands, but that it only describes what we can observe, not what really exists independent of observation. In this view, asking what a quantum particle is really doing when we're not observing it is a meaningless question. Reality only exists in the context of specific experimental arrangements. But this solution raises as many questions as it answers. If quantum mechanics only describes observations rather than reality itself, what determines which observations are possible? The Copenhagen interpretation seems to require arbitrary division between the quantum realm, where superpositions exist, and the classical realm of measuring instruments, where definite outcomes occur. But since measuring instruments are themselves made of quantum particles, this division appears to be a matter of convenience rather than fundamental physics. In 1957, Hugh Everett III proposed a radically different solution known as the many worlds interpretation. Everett suggested that quantum superpositions never actually collapse. Instead, every possible outcome of a quantum measurement occurs, but in separate, parallel universes. When you measure an electron's spin and find it pointing up, there's another universe where another version of you found it pointing down. The apparent collapse of superposition is just your conscious experience tracking one branch of an ever-splitting multiverse. The many worlds interpretation elegantly solves the measurement problem by denying that there is one. Quantum mechanics is perfectly deterministic. It's just that determinism applies to the universal wave function. That includes all possible worlds simultaneously. Every quantum interaction splits the universe into multiple branches, creating an incomprehensibly vast number of parallel realities where every possible quantum outcome is realized somewhere. Yet another approach, pursued by physicists like Roger Penrose and Stuart Hameroff, suggests that consciousness itself might play a fundamental role in quantum measurement. In their view, the collapse of quantum superpositions might be connected to specific quantum processes in the brain, perhaps in the microtubules of neurons, where quantum effects might persist long enough to influence neural processing. This would make consciousness not just an observer of reality, but an active participant in determining what becomes real through the act of observation. Recent experimental work has begun to shed new light on these profound questions. In 2011, researchers at the University of California, Santa Barbara succeeded in creating quantum superpositions in objects large enough to be visible to the naked eye, tiny mechanical resonators that were simultaneously vibrating and not vibrating. These experiments probed the boundary between quantum and classical behavior, testing theories about where and why quantum superpositions give way to definite classical states. The most sophisticated experiments now test the limits of quantum measurement in extraordinary ways. In 2016, researchers demonstrated interaction-free measurement, a technique that can determine information about an object without any photons actually interacting with it. This seems to violate our intuitive understanding of measurement, but it's perfectly consistent with quantum mechanics. The mere possibility of interaction can provide information even when no actual interaction occurs. Perhaps most remarkably, recent work on quantum non-demolition measurements has shown that it is possible to gain information about quantum systems without disturbing them in certain specific ways. These measurements exploit the subtle correlations that exist between different properties of quantum systems, allowing scientists to learn about some aspects of a quantum state while leaving other aspects completely undisturbed. This work reveals that the measurement problem is even more nuanced than originally thought. The act of measurement can selectively disturb some properties while preserving others. The measurement problem also connects to profound questions about time and causality in quantum mechanics. Some interpretations suggest that quantum measurements might involve backwards in time influences, where the choice of measurement somehow affects the past state of the system being measured. In 2007, Yakir Haranov and his colleagues developed a two-state vector formalism that treats quantum systems as being determined by both their past state and their future measurements, creating a picture of reality where effects can precede their causes in subtle but measurable ways. These experiments and theories reveal that the measurement problem isn't just about the technical details of quantum mechanics. It is about the fundamental nature of existence itself. The problem forces us to confront deep questions about the relationship between mind and matter, the nature of time, and the role of information in physical reality. If consciousness is required to collapse quantum superpositions, then mind becomes a fundamental feature of the physical universe rather than just an emergent property of complex matter. The measurement problem also highlights the limits of reductionist thinking. Classical physics encouraged us to believe that understanding the behavior of fundamental particles would eventually explain everything else. But quantum mechanics suggests that the whole might be fundamentally different from the sum of its parts. The act of observation creates a kind of irreducible relationship between observer and observed that cannot be eliminated through more sophisticated theories or better instruments. As we delve deeper into these mysteries, we encounter questions that stretch beyond physics into philosophy, cognitive science, and even theology. If every measurement creates the reality it observes, what does this mean for the nature of truth and knowledge? If consciousness plays a role in determining physical reality, how should we understand the relationship between subjective experience and objective existence? The measurement problem reveals that the universe might be fundamentally participatory, a cosmos, or observation, and reality are so intimately connected that they can't be meaningfully separated. This participatory universe would be one where the traditional boundaries between subject and object, observer and observed, mind and matter become fluid and interdependent. This profound mystery sets the stage for even deeper questions about the role of consciousness in quantum mechanics and the ultimate nature of the observer. As we'll discover, the measurement problem is just the beginning of a much larger mystery about how awareness itself might be connected to the fundamental structure of reality. Chapter 4. Observer Effect. The observer effect in quantum mechanics reveals one of the most profound and unsettling truths about reality. The act of conscious observation appears to play a fundamental role in determining what becomes real. This goes far beyond the simple fact that measurements disturb what they measure. Instead, it suggests that consciousness itself might be woven into the basic fabric of the universe in ways that challenge our deepest assumptions about the relationship between mind and matter, between subjective experience and objective reality. The most striking demonstration of the observer effect comes from the famous double-slit experiment, first performed by Thomas Young in 1801, but given revolutionary quantum significance in the 20th century. When electrons are fired one at a time toward two parallel slits, something extraordinary happens. If no one tries to determine which slit each electron passes through, the electrons create an interference pattern on the detector screen, the characteristic signature of wave behavior. But the moment you place a detector at either slit to observe which path each electron takes, the interference pattern disappears, and the electrons behave like classical particles. What makes this truly mysterious is that the electrons seem to know whether they are being observed. Even when the detectors are turned on, but no human is actually looking at the data they collect, the interference pattern still disappears. The mere possibility of observation, the fact that path information could be obtained, even if it isn't, appears to change the fundamental behavior of the quantum system. This suggests that consciousness and measurement are connected in ways that classical physics never imagined possible. The implications become even more staggering when we consider delayed choice experiments, first proposed by John Wheeler and realized experimentally by Alan Aspect and others in the 1980s. In these experiments, the decision of whether to measure which path a photon takes is made after the photon has already passed through the slits, but before it hits the detector. Remarkably, this delayed choice appears to retroactively determine whether the photon behaved as a wave or a particle during its journey. The future measurement decision seems to influence the past behavior of the quantum system. This temporal anomaly suggests the relationship between observation and reality might be even stranger than previously thought. In a 2007 experiment, Jacques et al. Demonstrated that entangled photons could exhibit delayed choice behavior across distances where classical signals could not possibly coordinate the observations. The measurement of one photon's path instantly determined the behavior of its entangled partner, even when the measurement decision was made after both photons had completed their journeys. The most puzzling aspect of the observer effect is determining what constitutes an observer. Early interpretations of quantum mechanics suggested that conscious awareness was necessary to collapse quantum superpositions. This led to the paradoxical conclusion that consciousness might be fundamental to the structure of physical reality, a complete reversal of the materialist assumption that consciousness emerges from purely physical processes. Eugene Wigner, one of the founders of quantum mechanics, took this possibility seriously in his 1961 paper, Remarks on the Mind-Body Question. Wigner argued that consciousness possesses a unique ability to affect physical reality through the collapse of quantum states. In his famous thought experiment, Wigner's Friend, he imagined a scenario where a conscious observer inside a laboratory performs a quantum measurement while Wigner observes the entire laboratory from outside. Wigner argued that from his external perspective, both his friend and the quantum system would remain in superposition until Wigner himself became aware of the measurement result. This creates an infinite regress problem. If consciousness is required to collapse quantum states, what about the consciousness of the person observing the first observer? The problem multiplies when we consider that according to quantum mechanics, all matter, including human brains, is ultimately composed of quantum particles that should exist in superposition until observed by consciousness. How can a quantum brain collapse quantum states if the brain itself exists in superposition? Modern research has revealed subtler ways that consciousness might connect to quantum mechanics without requiring such extreme conclusions. In the 1980s, Henry Stapp developed a detailed theory of how conscious intention might select which quantum possibilities become actual. Stapp's approach suggests that consciousness doesn't create reality, but rather selects from the range of possibilities that quantum mechanics makes available. The mind becomes a kind of filter that determines which potential futures become real through the act of observation and intention. Stuart Hameroff and Roger Penrose have proposed an even more specific connection between consciousness and quantum mechanics through their theory of orchestrated objective reduction, ORCOR. They suggest that consciousness emerges from quantum processes in the microtubules of brain cells, tiny structures that might be able to maintain quantum coherence long enough for quantum effects to influence neural processing. In their view, consciousness involves quantum computations that collapse according to Penrose's theory of objective reduction, creating moments of conscious experience. Recent experimental evidence has begun to support some aspects of quantum effects in biological systems. In 2007, researchers discovered that photosynthesis in plants appears to use quantum coherence to achieve near-perfect energy transfer efficiency. Quantum effects have also been implicated in bird navigation, enzyme catalysis, and possibly even in the processing of smell and taste. If quantum mechanics plays a role in these biological processes, it becomes more plausible that consciousness itself might involve quantum phenomena. The observer effect also raises profound questions about the nature of information and physical reality. Some physicists, following John Wheeler's it from bit hypothesis, suggest that reality might be fundamentally informational rather than material. In this view, quantum measurements don't just reveal information about reality. They participate in creating reality through the act of information processing. The observer effect would then represent the fundamental connection between information processing, consciousness, and physical existence. Quantum information theory has revealed remarkable connections between observation, information, and physical reality. The no-cloning theorem shows that quantum information cannot be perfectly copied, which means that every quantum measurement necessarily involves a trade-off between gaining information about some properties while losing information about others. This creates a picture of reality where information is conserved but constantly transformed through the process of observation and measurement. Recent advances in quantum computing have provided new perspectives on the observer effect. Quantum computers manipulate quantum superpositions to perform calculations that would be impossible on classical computers. But maintaining these superpositions requires incredibly precise isolation from environmental observation. The slightest interaction with the environment causes decoherence, collapsing the delicate quantum states that give quantum computers their power. This technological challenge has deepened our understanding of how observation and environmental interaction affect quantum systems. The observer effect also connects to the anthropic principle. the idea that the universe must have properties compatible with the evolution of observers like ourselves. If consciousness plays a fundamental role in determining physical reality through quantum measurement, then the existence of conscious observers becomes not just a product of cosmic evolution, but a necessary condition for the universe to have definite properties at all. This creates a participatory universe where consciousness and physical reality co-evolve in fundamental ways. Perhaps most remarkably, recent research on quantum biology suggests that the observer effect might extend beyond laboratory experiments into the living world. Some researchers propose that consciousness itself might be a quantum phenomenon that evolved specifically to take advantage of quantum measurement capabilities. In this view, conscious awareness would represent a sophisticated biological system for collapsing quantum superpositions in ways that provide survival advantages. The observer effect forces us to reconsider the fundamental nature of scientific objectivity. If consciousness plays a role in determining physical reality, then the traditional goal of eliminating subjective factors from scientific observation becomes not just impossible, but self-defeating. Science might need to evolve toward a more participatory model that explicitly includes consciousness as a fundamental factor in physical processes. This participatory approach to reality connects quantum mechanics to ancient philosophical traditions that emphasize the interconnectedness of mind and matter. But rather than representing a return to pre-scientific thinking, the observer effect suggests that science itself is pointing toward a more integrated understanding of consciousness and physical reality. As we explore these profound connections between consciousness and quantum mechanics, we encounter even deeper questions about the fundamental limits that govern what can be known about reality. The observer effect hints that these limits might not be external constraints imposed by nature, but internal features of the relationship between consciousness and existence itself. Chapter 5: Fundamental Limits. The universe operates according to absolute boundaries that no amount of technological advancement or theoretical sophistication can ever cross. These aren't temporary limitations waiting to be overcome by future discoveries. They're constitutional features of reality itself that establish permanent constraints on what can be known, measured, or predicted. Heisenberg's uncertainty principle was just the first glimpse into a much larger network of fundamental limits that govern the deepest levels of existence, from quantum mechanics to cosmology to the ultimate nature of information itself. Beyond the familiar position-momentum uncertainty relation, quantum mechanics reveals multiple complementary pairs of properties that cannot be simultaneously determined with perfect precision. Energy and time form another uncertainty pair, expressed mathematically as delta E delta T is greater than or equal to K2. This temporal uncertainty principle has profound implications for our understanding of causality and the nature of time itself. It means that energy can be borrowed from the quantum vacuum for brief periods, allowing particle-antiparticle pairs to spontaneously appear and disappear in what physicists call virtual fluctuations. These virtual fluctuations represent one of the most remarkable consequences of fundamental uncertainty. Even in completely empty space, a perfect vacuum with no matter or energy quantum fields must fluctuate according to the uncertainty principle. The ground state of reality isn't stillness but constant, unpredictable motion. These vacuum fluctuations have been directly measured through the Casimir effect, where two metal plates placed extremely close together experience a measurable attractive force due to the quantum fluctuations of empty space between them. The energy-time uncertainty relation also explains why we can never measure the exact energy of an excited atomic state if we want to know precisely when the atom will decay. The more precisely we determine the energy, the less precisely we can predict the timing of radioactive decay. This isn't just a measurement problem. It reveals that the universe itself operates on fundamentally incomplete information about its own future states. Radioactive decay remains genuinely random even from the perspective of an omniscient observer with access to all the information that exists. But quantum mechanics is just the beginning of reality's constitutional limits. In 1901, Max Planck discovered that energy comes in discrete packets called quanta, establishing that nature operates according to digital rather than analog principles at its deepest level. Planck's constant sets the fundamental scale at which quantum effects become important, creating an absolute minimum unit of action in the universe. This means that reality is fundamentally granular. There exists a smallest possible change, a minimum tick of cosmic time, and a basic pixel size of space itself. The speed of light represents another type of fundamental limit, not just on motion, but on the transmission of information and causal influence. Einstein's special relativity reveals that no signal, force, or influence can travel faster than light in vacuum. This creates absolute boundaries around each point in space-time, defining regions of the universe that are forever causally disconnected from each other. Events separated by space-like intervals cannot influence each other, creating a built-in isolation that prevents the universe from achieving global simultaneity or universal coordination. This light speed limit creates what physicists call horizons boundaries, beyond which information cannot reach us. The cosmic horizon sets the maximum distance we can observe in the universe, not because of technological limitations, but because light from more distant regions hasn't had time to reach us since the Big Bang. Even with perfect telescopes, there are parts of the universe that remain forever unobservable, not as a temporary limitation, but as a permanent feature of cosmic structure. The combination of quantum uncertainty and relativistic limits creates even more stringent constraints on information and measurement. The quantum Zeno effect demonstrates that continuous observation can actually prevent quantum systems from evolving. Frequent measurements can freeze a quantum state in place. But relativity sets limits on how quickly measurements can be repeated, creating fundamental trade-offs between the precision of measurement and the rate at which information can be extracted from quantum systems. Perhaps most remarkably, information theory itself reveals absolute limits on computation, communication, and knowledge processing. Claude Shannon's work in the 1940s established that all information can be measured in binary units called bits, and that every communication channel has a maximum rate at which information can be transmitted without errors. The Shannon limit isn't just about current technology. It represents a mathematical theorem about the fundamental relationship between signal, noise, and information that applies to any possible communication system. Rolf Landauer demonstrated in 1961 that computation itself has thermodynamic costs. Erasing one bit of information requires a minimum energy expenditure that cannot be avoided through technological improvements. The Landauer limit establishes that information processing is fundamentally connected to thermodynamics, meaning that perfect computation without energy cost, is as impossible as a perpetual motion machine. These information theoretic limits connect to quantum mechanics through the holographic principle, developed by Gerard 't Hooft and Leonard Susskind in the 1990s. The holographic principle suggests that all the information contained in a volume of space can be encoded on its boundary surface. This means that three-dimensional reality might emerge from two-dimensional information processing occurring at cosmic boundaries. If true, this principle would establish fundamental limits on how much information can be stored in any region of space. The holographic principle gains support from the study of black holes, which represent the most extreme information processing systems in the universe. Jacob Bekenstein discovered that black holes have entropy proportional to their surface area rather than their volume, suggesting that black holes process information in fundamentally two-dimensional ways despite being three-dimensional objects. Stephen Hawking's work on black hole evaporation revealed additional puzzles about information conservation that remain unresolved and may point toward even deeper limits on information processing in quantum gravity. Gödel's incompleteness theorems from mathematics reveal another type of fundamental limit, not on physical measurement, but on logical knowledge itself. Gödel proved that any sufficiently complex mathematical system must contain statements that are true but unprovable within that system. This creates absolute boundaries on what can be known through logical deduction, suggesting that perfect knowledge might be impossible even in the purely abstract realm of mathematics. The implications of Gödel's theorems for physics are still being explored, but they suggest that a theory of everything might be mathematically impossible. If physical reality is sufficiently complex, then complete understanding might require making assumptions that cannot be proven within the theoretical framework itself. This would make the dream of absolute physical knowledge not just practically difficult, but logically impossible. Recent work in algorithmic information theory has revealed even deeper connections between physical limits and computational limits. The concept of Kolmogorov complexity, the shortest program that can generate a particular string of information, establishes fundamental limits on data compression and pattern recognition. Most strings of information are incompressible, meaning they contain no hidden patterns that would allow them to be described more briefly than just listing all their details. This incompressibility principle suggests that most aspects of reality might be fundamentally random, containing no deeper patterns or laws that would allow perfect prediction or compression. The universe might be mostly filled with information that cannot be summarized, computed, or predicted, irreducible details that must be observed rather than calculated. Quantum error correction has revealed additional fundamental limits on information processing in quantum systems. While quantum computers can theoretically perform certain calculations exponentially faster than classical computers, they are also fundamentally limited by noise and decoherence. The threshold theorem in quantum computing establishes that quantum computation is only possible if error rates stay below certain fundamental bounds that are determined by the laws of quantum mechanics. These diverse fundamental limits, quantum uncertainty, relativistic horizons, thermodynamic costs, information bounds, logical incompleteness, all point toward the same profound conclusion. The universe operates according to constitutional constraints that establish permanent boundaries on knowledge, computation, and prediction. These limits aren't flaws in reality's design, but essential features that make existence possible in the first place. The existence of fundamental limits creates space for novelty, creativity, and genuine surprise in a cosmos that might otherwise be boringly predictable. Uncertainty allows for free will, innovation, and the emergence of genuinely new phenomena that cannot be calculated in advance. These limits make the universe participatory rather than mechanical, requiring ongoing interaction between different parts of reality to determine what becomes actual. As we delve deeper into these constitutional constraints, we encounter profound questions about why reality has the particular limits it does rather than others. The specific values of fundamental constants like Planck's constant and the speed of light determine the character of these limits, but explaining why these constants have their observed values remains one of the deepest mysteries in physics. Chapter 6: Reality's Boundaries. The universe is surrounded by invisible barriers that define not just what can be known, but what can possibly exist. These boundaries aren't merely practical limitations on human knowledge. They're constitutional features of reality itself that establish the rules by which existence operates. From the Planck scale at the smallest dimensions to cosmic horizons at the largest, reality is structured by limits that create the framework within which all phenomena must occur. Understanding these boundaries reveals why the universe has its particular character and why certain questions may be forever unanswerable. At the smallest scale, reality hits absolute boundaries defined by fundamental constants. The Planck length, approximately y-35 meters, represents the scale at which our current understanding of space and time breaks down completely. Below this scale, quantum fluctuations become so intense that space-time itself becomes uncertain. The Planck length isn't just a limit of measurability. It may represent the fundamental pixel size of reality, below which the concept of distance becomes meaningless. At the Planck scale, the geometry of space-time fluctuates so violently that causality, locality, and even the distinction between cause and effect may dissolve into quantum foam. Similarly, the Planck time, about y-43 seconds, defines the shortest interval during which any meaningful physical process can occur. This isn't just about the limits of our clocks. It represents the fundamental tick rate of existence itself. Events that would require shorter time intervals are prohibited by the basic structure of quantum mechanics and general relativity. The Planck time establishes a cosmic speed limit, not just on motion, but on the rate at which information can be processed by reality itself. These microscopic boundaries connect to cosmic scale limits in remarkable ways. The observable universe has a finite horizon determined by the finite age of the cosmos and the finite speed of light. We can observe approximately 46.5 billion light-years in any direction, not because space ends there, but because light from more distant regions hasn't had time to reach us since the Big Bang occurred 13.8 billion years ago. This cosmic horizon creates an absolute boundary around our observable reality. There are parts of the universe that are forever beyond our knowledge, not due to technological limitations, but due to the fundamental structure of space and time. But the cosmic horizon is more complex than a simple distance limit. The expansion of space itself creates multiple types of horizons that define different aspects of what can be observed or influenced. The particle horizon defines the maximum distance from which light could have reached us since the beginning of time. The event horizon defines the maximum distance to which we could send a signal that would ever reach its destination before cosmic expansion carries it away. These horizons create nested boundaries of accessibility that permanently divide the universe into regions that can and cannot interact with each other. Even more remarkably, cosmic expansion is accelerating due to dark energy, which means these horizons are shrinking over time. Galaxies that we can observe today will eventually disappear beyond our event horizon as cosmic expansion accelerates. Future civilizations will inhabit a universe where most of what we can currently see has become permanently inaccessible. The cosmos is developing cosmic amnesia, gradually forgetting its own history as accelerating expansion erases evidence of its past. The thermodynamic boundaries of reality create another set of absolute limits that govern what processes can occur in the universe. The second law of thermodynamics establishes that entropy, roughly speaking, disorder, must increase over time in any isolated system. This creates an arrow of time that distinguishes past from future and establishes fundamental limits on the efficiency of any energy conversion process. No engine can be 100% efficient. No information processing system can operate without generating waste heat. No process can completely reverse the flow of time. These thermodynamic limits connect to information theory through Landauer's principle, which establishes that erasing information requires a minimum energy expenditure. Every computation, every measurement, every decision involves irreversibly transforming information, creating waste heat that cannot be avoided. This means the perfect computation, information processing without energy cost, is as impossible as a perpetual motion machine. The universe itself operates as a vast information processing system, constrained by thermodynamic limits on computational efficiency. Black holes represent perhaps the most extreme example of reality's boundaries. The event horizon of a black hole creates an absolute boundary in space-time, a point of no return beyond which nothing, not even light, can escape. From the perspective of an outside observer, anything falling into a black hole appears to slow down and freeze at the event horizon, with information about its state becoming permanently inaccessible. But from the perspective of the falling object, it passes through the event horizon normally, experiencing nothing special at this cosmic boundary. This creates the black hole information paradox. If black holes eventually evaporate through Hawking radiation, what happens to the information that fell into them? Stephen Hawking's calculations suggest that black hole evaporation is completely random, destroying information in violation of quantum mechanics. But quantum mechanics requires that information be conserved, creating a fundamental conflict between general relativity and quantum theory. The resolution of this paradox may require understanding even deeper boundaries that govern the relationship between information, space-time, and quantum mechanics. The holographic principle suggests that these boundaries might be even more fundamental than previously thought. According to holography, all the information contained in a volume of space is actually encoded on the boundary surface of that volume. This would mean that three-dimensional reality emerges from two-dimensional information processing occurring at cosmic boundaries. If true, the holographic principle would reveal that what we experience as three-dimensional space is actually a kind of projection from fundamental boundary processes. Recent developments in quantum information theory have revealed additional boundaries that govern the relationship between measurement, entanglement, and correlation. The Cyrilson bound establishes the maximum strength of quantum correlations, showing that quantum mechanics allows stronger correlations than classical physics, but still prohibits the strongest correlations that would be mathematically possible. This suggests that reality operates in a middle ground between classical locality and mathematical extremes of correlation. These quantum information boundaries connect to the fundamental trade-offs that govern all measurement processes. The uncertainty principle establishes that gaining information about certain properties necessarily involves losing information about others. But deeper analysis reveals that this trade-off structure permeates all levels of physical reality, from quantum measurements to thermodynamic processes to cosmological observations. The existence of these boundaries raises profound questions about why reality has the particular limits it does rather than others. The fine structure constant, which governs the strength of electromagnetic interactions, has a value of approximately 1/137th. If this constant were significantly different, atoms couldn't form, stars couldn't shine, and chemistry couldn't create the complex molecules necessary for life. Similar anthropic constraints apply to dozens of other fundamental parameters, suggesting that the boundaries of reality are remarkably well-tuned for the emergence of complexity and consciousness. Some physicists interpret this fine-tuning as evidence for a multiverse, a vast collection of universes with different boundary conditions, where we naturally find ourselves in one of the rare universes with boundaries compatible with observation. But this explanation pushes the mystery back one level. Why should a multiverse exist? And what determines the possible range of boundary variations across different universes? Alternative approaches suggest that the boundaries of reality might be self-determining rather than externally imposed. The anthropic principle suggests that any universe capable of producing observers must have boundaries, compatible with the evolution of consciousness. This creates a participatory relationship between consciousness and cosmic structure, where the existence of observers helps determine which boundary conditions are realized. The boundaries of reality also establish the framework within which emergence and complexity become possible. Without uncertainty, there would be no room for novelty or creativity. Without thermodynamic limits, there would be no distinction between past and future, no possibility for irreversible processes that create new structures. Without cosmic horizons, the universe would have no way to develop local variation and complexity. Perhaps most remarkably, these boundaries make knowledge itself possible. In a universe without limits, everything would be knowable in principle, but nothing would be learnable in practice because there would be no finite processes by which information could be acquired and processed. The existence of boundaries creates the possibility of partial knowledge, gradual learning, and finite but meaningful understanding. These considerations suggest that the boundaries of reality aren't obstacles to knowledge but the preconditions that make knowledge possible. They create a universe where consciousness can emerge, where learning can occur, and where genuine discoveries remain possible. Understanding these boundaries helps us appreciate why ignorance isn't the opposite of knowledge, but its most essential companion. As we explore the implications of these cosmic boundaries, we encounter even deeper questions about the relationship between knowledge and existence, between what can be known and what it means to know. The limits that surround reality create the stage for a more profound mystery, the nature of knowledge itself, and why the universe seems to be structured in ways that make understanding both possible and eternally incomplete. Chapter 7. Knowledge Prison. We live inside a prison made not of walls and bars, but of the fundamental structure of reality itself. Every conscious being, from humans to any hypothetical superintelligence, exists within absolute boundaries that no amount of technological advancement or intellectual sophistication can ever breach. These aren't temporary limitations waiting to be overcome. They're constitutional features of existence that establish permanent constraints on what can be learned, computed, or understood. The universe has built-in ignorance that even omniscient observers cannot overcome, creating a cosmic knowledge prison from which no intelligence can ever fully escape. The bars of this prison are forged from the laws of physics themselves. Heisenberg's uncertainty principle ensures that even with perfect instruments and unlimited time, certain combinations of information remain forever inaccessible. You cannot simultaneously know the exact position and momentum of any particle, not because measurement disturbs the system, but because these properties don't simultaneously exist in definite form. This creates regions of genuine unknowability that persist even when observed by idealized, non-interfering observers. The speed of light creates another set of prison walls by establishing absolute boundaries around information accessibility. Even if you had perfect telescopes and unlimited computational power, vast regions of the universe would remain forever beyond your knowledge. The cosmic horizon ensures that information from the most distant parts of the universe will never reach any observer, regardless of how long they wait or how sophisticated their detection methods become. There are galaxies whose light will never arrive, stars whose existence will never be knowable, civilizations whose achievements will never be witnessed. But the knowledge prison extends far beyond these familiar physical limits. Gödel's incompleteness theorems reveal that even pure mathematics contains absolute barriers to knowledge. Any mathematical system sufficiently complex to describe basic arithmetic must contain statements that are true but unprovable within that system. This creates logical blind spots that no amount of mathematical sophistication can illuminate. Even a perfect mathematician with infinite time and unlimited computational resources would encounter true statements that remain forever beyond proof. The implications for physics are staggering. If reality is mathematical in nature, as many physicists believe, then Gödel's limits suggest that a complete theory of everything may be logically impossible. Any sufficiently comprehensive physical theory would necessarily contain true statements about reality that cannot be proven within the theory itself. The universe might contain aspects of truth that are permanently beyond the reach of scientific verification, even in principle. Computational limits create additional walls in the knowledge prison. Most mathematical problems are undecidable. There is no general algorithm that can determine whether they have solutions. The halting problem, proven undecidable by Alan Turing in 1936, shows that you cannot generally predict whether a computer program will eventually stop running or continue forever. This isn't just about current computational limitations. It's a mathematical theorem that applies to any possible computing device, including human brains and hypothetical superintelligences. These computational limits suggest that even with unlimited time and resources, much of mathematics would remain unknowable. The landscape of mathematical truth is filled with questions that no finite process can ever answer. This creates vast territories of ignorance that are built into the logical structure of mathematics itself, establishing permanent boundaries around what can be computed or decided. The knowledge prison becomes even more constraining when we consider the relationship between computation and physics. If consciousness involves computational processes, as many theories suggest, then computational limits become limits on possible consciousness itself. There may be thoughts that cannot be thought, ideas that cannot be conceived, and understandings that cannot be achieved by any possible conscious being, regardless of its level of intelligence or sophistication. Thermodynamic limits add energy-based walls to the knowledge prison. Landauer's principle establishes that every bit of computation requires a minimum energy expenditure that cannot be eliminated through technological improvement. This means that acquiring knowledge has an unavoidable thermodynamic cost. In a universe with finite energy resources, this establishes absolute limits on how much information can be processed, how many calculations can be performed, and how much knowledge can be acquired before thermodynamic constraints become prohibitive. The second law of thermodynamics creates temporal walls in the knowledge prison. As the universe expands and cools, approaching maximum entropy, the energy available for computation and information processing gradually decreases. Future civilizations will have progressively less energy available for knowledge acquisition, creating a cosmic deadline beyond which no new learning becomes possible. The universe is gradually shutting down its own capacity for knowledge creation and information processing. Quantum mechanics adds probabilistic bars to the knowledge prison. The fundamental randomness of quantum measurements means that certain aspects of reality are genuinely unpredictable, even with complete knowledge of initial conditions. Radioactive decay, quantum tunneling, and vacuum fluctuations introduce elements of pure chance that no intelligence can forecast. The universe contains irreducible randomness that makes perfect prediction impossible, even for an observer with access to all available information. Perhaps most remarkably, the knowledge prison appears to be self-reinforcing. The more we learn about the fundamental limits on knowledge, the more clearly we see that these limits are absolute and unavoidable. Each advance in our understanding of information theory, quantum mechanics, and computational complexity reveals new walls and barriers that constrain what can be known. Knowledge itself teaches us about the limits of knowledge, creating a peculiar recursive structure where understanding illuminates its own boundaries. The quantum measurement problem creates some of the most mysterious walls in the knowledge prison. If consciousness plays a role in collapsing quantum superpositions, then the nature of consciousness itself becomes entangled with the fundamental limits on physical knowledge. The observer and the observed become inseparably connected in ways that make objective knowledge about quantum systems impossible. Reality becomes participatory, where the act of knowing inevitably changes what is known. Information theory reveals that the knowledge prison has a finite capacity. The Bekenstein bound establishes the maximum amount of information that can be stored in any finite region of space. This creates an absolute limit on how much knowledge any physical system can contain, regardless of its organization or efficiency. Even a perfectly optimized civilization spanning an entire galaxy would be subject to this fundamental information storage limit. The holographic principle suggests that these information limits might be even more restrictive than previously thought. If all the information in a volume of space is actually encoded on its boundary surface, then the amount of knowledge that can be stored in any region scales with area rather than volume. This would make the knowledge prison even smaller than classical physics would suggest, establishing tighter constraints on how much information reality can contain about itself. Recent work in quantum information theory has revealed additional structural features of the knowledge prison. The no-cloning theorem shows that quantum information cannot be perfectly copied, which means that acquiring knowledge about quantum systems necessarily involves trade-offs where gaining some information requires losing other information. The knowledge prison operates according to conservation laws that ensure perfect knowledge remains impossible. Quantum error correction establishes that even the knowledge that can be acquired is subject to fundamental noise limits. All information processing in quantum systems must contend with decoherence and errors that cannot be completely eliminated. This means that even the information that lies within the accessible regions of the knowledge prison is subject to uncertainty and degradation that no error correction protocol can completely prevent. The existence of the knowledge prison raises profound philosophical questions about the nature of truth and understanding. If there are aspects of reality that are permanently unknowable, what does this mean for concepts like truth and knowledge? Can something be true if it is forever beyond the possibility of verification? Does knowledge have meaning if it is surrounded by vastly larger territories of necessary ignorance? Some philosophers argue that the knowledge prison makes truth itself participatory. If reality can never be fully known from any external perspective, then truth becomes something that emerges through the interaction between conscious observers and the aspects of reality they can access. Knowledge becomes less about discovering pre-existing facts and more about participating in the creation of meaning through the act of observation and understanding. The knowledge prison also creates space for mystery, wonder, and genuine surprise. In a universe where everything could be known, there would be no room for discovery, creativity, or the unexpected. The existence of permanent boundaries around knowledge ensures that reality always contains more than can be understood, creating an inexhaustible source of questions and possibilities. Perhaps most importantly, the knowledge prison ensures that consciousness remains meaningful. If everything could be known, there would be no role for awareness, choice, or understanding. The existence of limits creates the framework within which consciousness operates, establishing the conditions under which learning, discovery, and meaning become possible. As we come to terms with life inside the knowledge prison, we begin to see that these limits aren't obstacles to understanding, but the preconditions that make understanding possible. The bars of our prison are also the framework that supports consciousness, knowledge, and meaning. Understanding the structure of our cosmic confinement becomes a pathway toward appreciating the remarkable character of existence itself. Chapter 8. Cosmic Uncertainty. The universe itself operates on incomplete information. This isn't a temporary condition waiting to be resolved by future discoveries. It's a fundamental feature of cosmic architecture that makes existence itself possible. From quantum fluctuations in the vacuum to the large-scale structure of space-time, uncertainty permeates every level of reality, creating a cosmos that continuously surprises itself through the emergence of genuinely novel phenomena that could not have been predicted from earlier states. At the quantum level, the vacuum of empty space seethes with uncertainty-driven fluctuations that create particle-antiparticle pairs from pure nothingness. These virtual particles exist for impossibly brief moments before annihilating each other, but their existence is real enough to produce measurable effects. The Casimir force between closely spaced metal plates demonstrates that quantum uncertainty generates actual physical forces from apparently empty space. The vacuum itself is uncertain, constantly fluctuating in ways that make perfect nothingness impossible. These quantum vacuum fluctuations may have played the central role in creating the large-scale structure of the entire universe. During cosmic inflation in the first moments after the Big Bang, Quantum uncertainty in the inflation field was stretched to astronomical scales, creating the tiny density variations that eventually grew into galaxies, stars, and planets. The cosmic web of galactic superclusters that spans billions of light years may have originated from quantum uncertainty operating at the Planck scale. The universe's largest structures are monuments to the power of microscopic uncertainty amplified to cosmic dimensions. But uncertainty operates at every scale of cosmic organization. Stellar evolution involves genuinely unpredictable processes where small quantum fluctuations in nuclear reactions can cascade into major changes in a star's structure and lifetime. The exact moment when a star will explode as a supernova cannot be predicted with certainty, even with perfect knowledge of the star's initial conditions. Stellar death involves quantum tunneling processes that introduce irreducible randomness into the timing and character of these cosmic explosions. The formation of planetary systems similarly involves uncertain processes where tiny variations in initial conditions can lead to dramatically different outcomes. The gravitational interactions between forming planets create chaotic dynamics where quantum uncertainty gets amplified through sensitive dependence on initial conditions. Whether a planetary system develops stable orbital configurations or experiences catastrophic collisions may depend on quantum scale uncertainties that occurred during the planet formation process. Even more remarkably, cosmic uncertainty appears to be increasing over time rather than decreasing. As the universe expands and cools, quantum systems become increasingly isolated from each other, making quantum measurements less likely and allowing superposition states to persist for longer periods. The cosmic expansion that we observe may be driven by dark energy whose nature remains completely mysterious and whose behavior appears to involve genuine uncertainty about the future expansion rate of space itself. Dark energy represents perhaps the most profound example of cosmic uncertainty in contemporary physics. Making up approximately 68% of the universe's total energy density, dark energy appears to be causing space itself to expand at an accelerating rate. But the physical nature of dark energy remains completely unknown. It might be a cosmological constant representing the energy density of empty space itself, but calculating this energy density from quantum field theory yields results that disagree with observations by a factor of 10,120, arguably the worst prediction in the history of physics. Alternative theories propose that dark energy might be a dynamic field that evolves over time, introducing uncertainty into the future expansion history of the universe. If dark energy is dynamic rather than constant, then the ultimate fate of the cosmos becomes genuinely uncertain. The universe might continue expanding forever, or it might recollapse in a big crunch, or it might experience a big rip where accelerating expansion eventually tears apart all bound structures, including atoms themselves. The uncertainty inherent in dark energy makes the cosmic future fundamentally unpredictable. Dark matter adds another layer of cosmic uncertainty. Comprising approximately 27% of the universe's mass energy, dark matter has been detected only through its gravitational effects. Despite decades of intensive searching, no dark matter particles have been directly observed, and we remain completely uncertain about their fundamental properties. The dark matter might consist of exotic particles that interact only weakly with ordinary matter, or it might represent a modification of gravitational physics that we don't yet understand. The cosmic microwave background radiation preserves information about quantum uncertainty from the earliest moments of cosmic history. The tiny temperature fluctuations observed in this ancient light represent fossilized quantum fluctuations that were stretched to cosmic scales during inflation. These fluctuations are genuinely random, containing information that could not have been predicted from any earlier state of the universe. The cosmic microwave background is essentially a baby picture of quantum uncertainty written across the entire sky. Black holes introduce additional uncertainty into cosmic evolution. When matter falls into a black hole, information about its quantum state becomes inaccessible to outside observers, creating what appears to be a loss of information that would violate the fundamental principles of quantum mechanics. The black hole information paradox represents a conflict between general relativity and quantum mechanics that has profound implications for our understanding of space, time, and information. Hawking radiation suggests that black holes slowly evaporate by emitting thermal radiation that appears to be completely random. If this radiation truly is random, then black holes destroy information, creating genuine uncertainty about the past history of matter that has fallen into them. But if information is somehow preserved in the Hawking radiation through subtle correlations that we don't yet understand, then black holes might be the universe's most sophisticated information processing systems, transforming information in ways that create new forms of cosmic uncertainty. The cosmic horizons created by the finite speed of light and cosmic expansion introduce observational uncertainty that can never be overcome. There are regions of the universe that will forever remain beyond our observation, not because of technological limitations, but because of the fundamental structure of spacetime. This creates permanent blind spots in our cosmic knowledge where entire civilizations might rise and fall without any possibility of detection or communication. Quantum gravity effects at the Planck scale introduce uncertainty into the very structure of spacetime itself. At distances of approximately 10 to 35 meters and times of y-43 seconds, quantum fluctuations make the geometry of spacetime genuinely uncertain. Space and time themselves may consist of discrete, quantized units that fluctuate according to quantum uncertainty principles. The smooth spacetime of classical general relativity may emerge from an underlying foam of quantum geometric uncertainty. Recent observations of gravitational waves by LIGO and other detectors have opened new windows into cosmic uncertainty. These ripples in spacetime itself carry information about some of the most violent events in the universe, including black hole mergers and neutron-star collisions. But gravitational wave astronomy also reveals that spacetime is constantly bathed in stochastic gravitational wave backgrounds created by countless uncertain processes throughout cosmic history. The multiverse hypothesis suggests that cosmic uncertainty might operate on scales vastly larger than our observable universe. If cosmic inflation creates an infinite number of bubble universes with different physical laws and constants, then our entire observable cosmos represents just one uncertain realization among an infinite number of possible universes. The fundamental parameters that govern our physics, the strengths of forces, the masses of particles, the rate of cosmic expansion, might be genuinely random variables that take different values across different regions of an infinite multiverse. Even more speculatively, some theories suggest that the laws of physics themselves might be uncertain and evolutionary. Rather than being fixed eternal principles, physical laws might emerge and evolve through cosmic history in ways that introduce fundamental uncertainty into the character of reality itself. The universe might be learning its own laws through the process of cosmic evolution, with each epoch introducing new uncertainties and possibilities. The anthropic principle adds another dimension to cosmic uncertainty. The fact that we observe a universe capable of supporting conscious observers might be the result of observer selection effects operating across an uncertain ensemble of possible universes. We find ourselves in a cosmos with particular uncertain properties, because those properties were necessary for the evolution of observers capable of making such observations. This creates a participatory relationship between consciousness and cosmic uncertainty. The existence of conscious observers might be both a product of cosmic uncertainty and a factor that helps determine which uncertain possibilities become realized through the act of observation. Consciousness becomes not just a witness to cosmic uncertainty, but a participant in the cosmic process by which uncertain possibilities become definite realities. Perhaps most remarkably, Cosmic uncertainty ensures that the universe remains capable of genuine novelty and surprise. In a perfectly deterministic cosmos, everything that ever happens would be implicit in the initial conditions, making cosmic history a boring unfolding of predetermined patterns. But uncertainty creates space for genuine creativity and emergence, where new phenomena can arise that could not have been predicted from earlier states. Cosmic uncertainty also ensures that consciousness and intelligence remain meaningful. In a universe where everything could be predicted in advance, there would be no role for awareness, choice, or understanding. Uncertainty creates the framework within which consciousness operates, establishing the conditions under which learning, discovery, and decision-making become possible and meaningful. The existence of cosmic uncertainty reveals that the universe is more like an ongoing creative process than a mechanical system running according to predetermined rules. Reality continuously creates itself through the resolution of uncertainties, making existence itself a form of cosmic improvisation where the script is being written in real time through the interaction of uncertain processes.